Well, thank you everyone to stay until the very last talk of this, and followed by a panel discussion, of course, so don't go away. And also thank you to follow this last session, because it was a little bit of a mix, but the idea was to have general discussion about tools, methods, technologies that can help us in better engaging with the policymaker and the society at large. And I mean, tools on everything: modeling tools, data collection and processing tools, but also tools to better engage. Sysketch we had just seen before, but also tools like a more narrative tools like Marcos presented to us, which I say it again, I think should be the standard on the way we present things to policymakers. So this one tried to put all together, but very much focus on the technology element. As you can see, robotics, AI, and modeling on integrated ecosystem assessment. And you might wish that there was no wheel attached to that, but here it is. And now it is the last wheel that you will see in this symposium. I think 6 talks ago, someone said, "Oh, this will probably the last one." No, all the talks had it. So in this loop, where the new technology might help, I think, for data collection and processing, we all know that actually it can be done at different levels, expert judgment, totally qualitative way. Quantitative is kind of where we are aiming to, and that requires a lot of data to actually extract trends, indicators, etc. AI or artificial intelligence tools, machine learning, a bit advanced type of machine learning, and different type of modeling. Also, what I will talk a little bit about is this mix between mechanistic models, so process-based models, what Mike has shown, that's a very mechanistic models, or data-driven models. Data-driven models are more like the type of the machine learning approach. You put a lot of data in it and try to extract information or try to make forecast. And then there is something in between. You can couple both the process-based and the AI to improve both the analysis of processes, but also to better improve forecast. I'll show something on that too. And then the last one, in terms of technologies for better engaging, there are different kind of concepts around, different kind of wishes in terms of what the digital twin of the ocean, which is a large-scale initiative in Europe, probably know. If you don't, now you know. There's a lot of money invested in this direction at European level. Different people translating different concepts. There is a group that says this is just a new way of funding numerical models, which might be true. In terms of the policymakers, is actually a tool to transfer some of the knowledge we generate in science into an accessible format for policymakers and decision makers in general, to explore scenarios, to test ideas, and to better make decisions based on the best scientific knowledge. So this is, to me, translated to something how to better access stakeholders. So I mentioned this already. This is actually extracted from some of the deliverables of Mission Atlantic. If you want to do an analysis of trends across the sectors, across the pressures, across the ecosystem components, you want to do it quantitative, you better have data. And these data, they have to come at a relatively high let's say, frequency, and also good quality in general. I think this one is the case for the Norwegian Sea, which is probably the best we have in terms of the amount of data we have available. And then we try to put them together, try to analyze this data and extract indicators, try to define, trends and changes at the ecosystem level. So how these data are collected? 90% of the time they are collected using ships or ship-based monitoring activities. And you probably all know that, they are a high cost. They involve, a lot of logistics, a lot of people involved. Of course, they also have a lot of processes that can be used and can be monitored. But still, the trend at the moment is to, if we want to expand the ability to monitor the system, we need to reduce the cost. We need to find alternative solutions. It has limited coverage, maybe is also connected to the high cost. And also there are gaps, typically temporal gaps. People, they don't go at sea, or they don't tend to go at sea when the weather is really bad, or in locations that are just very extreme or remote. So there are issues related to the traditional monitoring, and that's the reason why new technologies could come at hand. I mean, autonomous systems, autonomous vehicles, both surface vehicles, aerial vehicles, underwater vehicles. In the historical period we have today, I think I always make the comparison, the development of sonar, for example, of underwater vehicles like submarines back in the days. They are always linked to period of wars, and now, unfortunately, is a period of growing tensions. And I think the technology of where things are invested are really on these autonomous systems. Well, we also take things from the medical sector, I think, in other direction. But in this case, I think what we will see in the next 5 to 10 years is a big development of autonomous systems. So we better be prepared on that and try to see how we can use this to solve some of our issues, which are about monitoring. So I mentioned already autonomous systems. I mentioned already the use of AI, because with the ability to explore more the ocean, of course, also gives us a lot of data. So there are maybe tools developed in the AI, the artificial intelligence area, which is a very big basket of many things. We can use that to extract some knowledge, as I mentioned before, and then provide them on these digital twins. So I want to put that in examples, some examples coming directly from Mission Atlantic, because we had the idea to explore some of these technologies to better observe the ocean. One of it was what is called the wave glider that you can see up there. I think I will try to use this. Yeah, this one actually is a deployment. I can't remember if I was there when we did that, but is the tool, the wave glider itself, that is deployed at sea in Gran Canaria, I think, or at the Azores. And maybe Pedro can help me on that. Is that the Azores? Yeah. So, and we deployed, actually, the map is here. We deployed it in July 23, and it traveled autonomously, of course, in this along this transect. Here we had some ideas that didn't really work, but and then we ended up in Gran Canaria. I can't remember how many weeks it was at sea. The new thing is that it was carrying acoustic transducer behind, making, I mean, it's a EK80, so it's a eco sounder or eco sonar. It's detecting the echo of particles that are in the water or stuff that are in the water. So the idea was to look at fish or anything that was backscattering. But at the same time, we had the possibility, I think in 2023 was also a kind of a heat wave in the Atlantic Ocean. We had extreme temperatures, like up to 29 in places that were not supposed to have that high temperature. So there are interesting amount of data that actually emerged from this activity, although the focus was really about testing the technology. These are one of the first examples we got in terms of the acoustic data analysis of migrations of something, most likely fish, in the water, going from 100 meter all the way down to the detection limit of the transducers we have used, which is about 250, 300 meters, at the sunrise and sunset, doing the other way around, going from the deep to the upper part. And we have these along all these transects, so we are now trying to classify this behavior and try to see if there are common patterns for different biogeographic regions. The technology we thought was very developed. We ended up that actually we had a lot of issues with system integrations and how to make it work. So yeah, let's say that now that the system has been tested and we know when it works and when it doesn't. And yeah, next round, I think we will do it better. So the deep sea glider, I think that one is also a very positive story emerging from Mission Atlantic. It's a deep sea glider, so it's a glider. Ralph is here in the room. If you want the details how it works, you can ask him. But basically, it's launched from a small boat, and it starts making deep dives to the bottom, typically collecting data in terms of temperature, salinity, and other physical parameters. In this case, the idea in the project was to develop a camera system that was tailored to this vehicle to collect images at the very bottom of the ocean and use these images for validate some of our models. So the camera system that was developed looks like this, is very modular, so it is attached to the glider there. And this is one of the examples of the type of mapping we can perform. With this one, I think it was used relatively shallow area so far. This is 500 meters. So we had few tests at shallow areas, but this one actually is a proper test at very deep. And it's not an easy thing to collect images at high resolution at that depth, and also at relatively small cost. We have seen before collections with ROVs. Typically that requires a big vessel, staying at sea for a few days, operating this with a professional. In this case, the operation is cheaper somehow. But in terms of autonomy in the ocean, I think the real revolution came with the ARGO float, which is an ARGO, probably everyone knows about it. We actually have one just in the room there, in case you are curious to see how it looks. The ARGO is a program on its own, actually. The profiler is this device here, and is left in the ocean, and then it kind of is programmed to sink at a given depth, drifting for a few days, sinking fast down to 2,000 meters, and then going up to make a profile. And when the profile is completed, the data are transmitted by satellite, and then the cycle is repeated. So this was launched like 20 years ago, and it really created a revolution in the way we observe the ocean, giving us a lot of data that we have used, extensively. And there are discussions about, of course, biogeochemical ARGOs, so mounting not only CTD or temperature, salinity, and light, and things like that, but actually have a full set of biogeochemical characteristics. This already has been around for a few years. It still costs a lot, but I think it's an interesting technology to scale up. There are discussions about the deep ARGO, so going further down than 2,000 meters to make samples at a very high deep. What we have been working on is actually a shallow water concept, which is basically a modification of the ARGO structure. At the bottom, we have like a gear like this with spikes, and these spikes are designed to attach to the bottom. So the actual device is parked at the bottom, and then makes the same way profiles at a specific at regular time. We have deployed it in the Baltic Sea, which is very shallow, at a depth of 50 meters, and not the 1,500 that the ARGO is designed for. And we have been able to, of course, one issue when you deploy it in coastal water is that you want to keep it there, because you don't want to end up, in this case, in Russia, for example, but not even Sweden. We prefer to have it in Denmark. So, and we have developed a system to keep it under control. And with a full biogeochemical set, you get very high resolution data. Every 5 days, you get a profile. You can see all the transition. This one is an example for a full year, November 23, I think it was. And the advantage of this is that not only it acts as a profiler, it also acts as a bottom mooring. And in the Baltic, the bottom properties are very interesting. So bottom mooring means that it was sampling the bottom of the ocean every hour and transmitting the data through satellite. And this one is kind of a very operational device, because everyone can buy one of these, make some modification, and then deploy it in the sea and start collecting data basically from day one. And you don't need to go at sea any longer. It lasts for 4 years and gives you a lot of data. I added this after the talk we had before on ROV bottom detection. It's a bit long. I'll go over time, but so this is an ROV a sampling of the bottom. So the idea was to bending mapping with ROVs. I mean, they're kind of labor intense. Still, I mean, it's much better to send an ROV than sending a diver, especially in the North Sea, which is like here, because the visibility looks like this. There is maybe something with the projector, but it really looks bad. I mean, you don't want to send anyone down there. What? Yeah, it's much better. Yeah, but this one is not that it's an artifact of the Aqua. It's just that the visibility down there, I don't know how the Celtic Sea was so nicely framed, but because maybe it was much deeper. This one is not that deep. So the technology we have developed is that not only the scanning and how to operate in these kind of extreme conditions. If it goes to the next one, let's have a look. Yeah, so from that kind of long video we create, and it's done with a special camera with 6 type of cameras, and we have maps like this, which are full three-dimensional maps, and typically it's much better to see things on a map than having to see hours of videos. I think in the Caltech it was like 300 hours of videos. I think that's that. So it's much easier to make things on a map, and then applying on these maps different type of artificial intelligence for object identifications, measuring of patches, or measuring, species. In a 3D context, of course, in 2D you can think that a rock, it could be a hole, and then you can count that as a hole as a nephrops hole. In 3D, you can actually distinguish between the hole and the rock. So there are advantages in using these three-dimensional type of reconstructions. Like, for example, measuring stuff, everything will be basically geo-referenced, and also with the scale for measuring it. Yeah, so I added that. Just let me see if I can show you. And then with this orthophoto, of course, you get additional features like a better depth measurements at the given locations. So in terms of modeling, as I promised, there are a lot of innovation there, and really will take a lot of time to tell how the different tools of AI that has been developed, most often in different contexts, finance and banking and security now. Some of these tools have been used in oceanography to do stuff, and it shows actually quite good skills. Of course, in oceanography, in ocean context, we don't really have the big data level that others might have. The only source of big data for us could probably be remote sensing and other models, like the process-driven models. These models, like the one Yuri has developed, they produce terabytes of data, and no one will ever look at them. So the AI... well, we look at a few gigabytes of data, but processing terabytes of data with regular tools is impossible. Unless you have a very specific question, then you go there and you check for it. So the AI can be used to extract features like anomalies or changes or things that actually you might not even think about. So we have used it in different contexts in Mission Atlantic, but I'll skip this over and focus on what we have done in terms, for example, of bias correction of Earth system models. So there was a lot of discussion about the use of different forcing from Earth system models, the CNRM and the GFDL. And we don't know which one is true. Let's say that GFDL is giving for a given value in a given location this type of trend. The CNRM is doing this. And maybe observed variable, which could be some satellite or remote sensed variable, temperature or ocean color or others. They do like this. So which one is better? The idea was to correct this using machine learning. So trying to train a network where you have in input the output of these process-based models and force them to reproduce the observed value. When you do that exercise, basically the network itself becomes like a bias corrector, which is not a standard bias corrector because it's adapted to the specific locality and the specific time. So each model might have different skills in different places at different time, and these nonlinear kind of corrections will reproduce that. So for example, this is an output of the model we have got. So the lines here are, the red is one model, the purple is another one. The yellow, which is almost invisible, is the observation. And actually, the QGCNN, which is the one we have developed, gives a much better estimates of the observed value respect to the other two models. And also gives uncertainties around that. So what's the point? Once you have this trained for observations, then you can use this one to correct the future predictions of these two models. Yeah, and as I said, different models, they perform differently in different locations. So it's not that one is much better than the other. It really depends on localities. So all these actually, they are key components. So better data, better real-time data, better tools for modeling and processing the data. They are all components of this digital twin, which is really in the eye of the Commission, at least, dedicated to engage with stakeholder. And I think for us, the digital twin, in terms of us, a community working on integrated ecosystem assessment, can really give the link with the decision maker if we are ready to exploit its features. And in the context, the editor is the program behind that. I think there are things that resonate with what we have heard before in terms of a data lake. So try to link all the data that are available online in a common framework. It's only an engine at the moment. There is no visualization as such, but the concept is also to develop maybe visualization tools. There is a very good example of how to use this in terms of integrated ecosystem assessment in another project, which is called Bridge. And it was similar to Mission Atlantic, but focusing on the Black Sea. And some of the partners, I mean, SUSE has been contributing to that. Can't remember of others. No, well. But anyway, they have developed this online access of the data that they have developed for the Black Sea in terms of biogeochemistry, high trophic levels, observations, and also models. A resilience assessment and cumulative effect assessment. And I think it's almost like a blueprint of what the components should be to offer this as a tool for policymakers to make a decision about spatial planning, for example. Yeah, I wanted to show this very briefly. You can also look at it outside this room, but this is another concept of digital twin, which is at much local, smaller scale. And for example, it's something we have done for Copenhagen Commune to digitalize the Copenhagen Commune. And we went there with some autonomous system that is also outside the room here. So we are kind of sitting somewhere here. Well, let's see if this one starts. It's south of Copenhagen. And the idea was to integrate the scanning of the seafloor with the scanning of all the buildings to produce a three-dimensional map, which is coming up now. So first of all, this map can be done in like half an hour for this small locality. And the second is that the map goes straight into a web service that the users can start exploring in a dynamic way, try to identify features and things. The specific idea here was to identify hidden pipes. Yeah, it's a long story, but these are a canal where people are swimming and sometimes they should not. And the commune does not understand where the pollution is coming from. And they asked us, are there pipes there? Yeah, so with this one, then the idea was to link it to numerical models for pollution. So you can go from a pipeline of a highly resolved data to numerical models to then provide something back to the society, which is about, okay, swim or not, when, and when you can do that. And that the same type of pipelines from data collections to modeling and providing services to the society is what we should look at in terms of the next generation of integrated ecosystem assessment. And I think that's it. I'll stop also because I talked for 23 minutes. And take-home message, I think I've said them all together before. And of course, I mean, the real key message is that there is such, let's say, push for developing new autonomous technologies for other sectors, which I think could be beneficial to address some of the problems we have in ocean observations. Yeah, that's it. Thank you.
So thanks a lot, Patrizio. And I think it was worth dragging over a couple of minutes. I think it was quite thrilling to see, and this visions for how we can even further use this kind of new technology and apply it in various contexts. So are there any questions, any comments? Yes, please, Yuri.
No, is the question completely out of ignorance, because it was on the observation side. The benefit of the coastal ARGO that is basically stationary in one place versus a profiling buoy.
Yeah. So the profiling buoys, let's say coastal ARGO is much cheaper than any profiling buoy that is on the market. And also these profiling buoys, typically they don't have the same level of reliability in terms of performing in some strong currents, like the Baltic one, that can have like meters per second velocity. They get entangled. And with this one, which has no tether, but some smart control of the position, we don't have that risk. Of course, the major risk is that we lose it. But there is a GPS attached, so worst case scenario, we go and take it back.
Thanks.
I think there's an idea of smart monitoring. I mean, you can put a sensor, I guess, anywhere you'd like, but there may be areas that have a large representation of a much larger scale. So it would be useful to use existing data or to do purpose deployments where you can consider areas that give you much more broader or much broader information. And so that sort of background would be and should be essential to any type of monitoring program. So you criticize some of the ship-based sampling, but in fact, you know, there may be a lot of redundancy in sampling so many sites, when in fact it could be that a few key sites represent, you know, hundreds of kilometers, say in terms of fish distribution or particular abundances or whatever. So that kind of data exploration in advance of deployment of any type of sensor, I think would be essential.
Yeah, I totally agree. I mean, I was criticizing for the type of scaling up we need to do, especially in coastal areas, indeed. Of course, there is no value to sample, I don't know, temperature every hour at 2,000 meters. I mean, you better go there once per year, it's enough. But yeah, this type of where to place them, that's actually something that we try to explore, also in terms of, I didn't show that, but we try to reconstruct the inner part of the ocean using satellite and machine learning coupled with ARGO floats. And that can give you an estimate of where you make most of the errors and where you need more observations to actually predict better. Yeah, that's a good point.
Cool. Any other comments? Yes, please. I think there's, yeah, we can start over here.
Just a comment on that. From the physical oceanography, what we do is we use actually model uncertainty outputs to guide our observations to improve actually the models. And so we don't go blind into and just let's try sample there and doing that. So that's actually a big effect. And another comment on the ships. I mean, we still need ships, obviously, and you were right saying it, but what we can increase our ability to use ships efficiently. So by doing multiple things at the same time, having an autonomous system out, that will increase the efficiency and actually then, you know, helps us all getting more data for the same amount of ship time.
Yeah, I agree.
Cool. And a final comment, I think it was Jim.
Thank you. Thanks, Patrizio. You have used artificial intelligence to compare the two models and then correct for the projection. When you use to correct this to the future, is like a regional downscaling? Or can you explain a bit more?
No, we don't do any downscaling. I mean, the idea is that we know for sure, based on the present state and the comparison between the observed data and some of this model output for present state, that neither of the two models are always correct. They might be correct in some area, at some locations, and at some time, or very wrong at the same location sometimes. So the idea is to correct for this deviation. So they typically have an offset or they have a change in the dynamic. And to use the AI trained on the observations and using an input, those two models, to basically have at the end a network that is trained to correct them for the present state. And we apply the same correction for the future. There might be an issue in terms of trends and things. I mean, for the type of test we have done, because we have done this in the typical way, having training set, a validation set, and a test set, based, of course, on the availability of the observations. The trend itself doesn't seem to be a big issue. So we assume that this is not going to be a big issue for the 2070 horizon that we have used in the project.
Thanks a lot. Thanks a lot to all the speakers.